Okay, page 21. The last part of this chapter is connecting graphs and rational equations. So the first question says determine the roots of the rational equation algebraically. So the roots are the zeros, the solutions. They're also the x-intercepts. Oh.
Lyndon, why are you not here today? Oh, hold on.
Okay, so the roots are the zeros, they are the solutions, they are the x-intercepts of a graph. So if we want to find the roots or the x-intercepts algebraically, remember the x-intercepts are always found where y equals 0. Okay, so we want to solve this equation. We've already got y equaling 0. There's Chance. Don't make me come over there. Chance. Don't lie to me either because you're making it worse. You're not sorry. You're going to do it again. Right, exactly. So, if we're going to solve this, we're going to get rid of the denominator, the x plus 2, by multiplying all the terms by x plus 2. So, let me just rewrite this equation out so I have room to do that. So we're going to multiply all the terms by the denominator, the common denominator, but there's only one denominator, which again is x plus 2. So all of the terms have to be multiplied by the x plus 2, including the 0 on the right, but that doesn't change anything. 0 times anything is still 0, but what it does do is it gets rid of the x plus 2 denominator for that second term. So now if you multiply out what's left, you'll have x squared plus 2x plus 6 minus 5x minus 10 equals 0. So what we have here is we have a quadratic. We have x squareds and we have x's. So normally when we're solving quadratics, we make them equal to 0, and then we see if we can factor them. So the 2x take away the 5x is the minus 3x, and then you have 6 take away 10, which is minus 4. So these are x squared minus 3x minus 4, which can be factored. The factors would be x minus 4, x plus 1. So that gives us answers for x to be positive 4 and negative 1. So those should be the x-intercepts. Those should be the solutions, the zeros, the roots of the equation. And we can confirm them by graphing it. We can graph it in our calculator. So we're going to have x plus, whoops, try that again, x plus. So I got a rational term here that I'll put in brackets to keep it together. 6 divided by, and then the denominator is x plus 2. Close the bracket on the x plus 2, close the bracket on the rational term, minus 5, enter. Zoom 6 to set our windows back to standard settings. And if we didn't already have the x-intercepts, we could find them by finding the zeros, second function trace. Number 2 is 0. I'll put my left boundary at negative 2, my right boundary at 0, and then my guess. It gives me my answer of negative 1. But we already had them, right? And negative 1 is confirmed. The other one we have is positive 4, so we're in that trace mode already. If we go 4, enter, It'll go there on the graph, and because it shows the y value is 0, that confirms that that is the other x-intercept. So the connection between the roots of the equation and the x-intercepts of the function, they are the same. The same thing. If you want the roots, the zeros, the solutions of an equation, they are the same thing as the x-intercepts. Right, so this is how we can solve these rational equations. We can do them graphically, as well we can do them algebraically. And no matter which way you do it, you can always check. If you do it one way, you can check doing it the other way. In the first example, we did it algebraically first, and we checked graphically. This one, we're asked to do it graphically to the nearest hundredth, because the answers are going to be probably irrational, but then we'll check them algebraically. So that first term, the term on the left, is a rational expression, so I need brackets for that. A second set of brackets to keep the numerator together, and that's divided by, in brackets, 3 minus 2x. Close the bracket on the 3 minus 2x. And then close the bracket on the rational expression part. And the other side of this is x minus 1. So in the last example, we had one equation equal to 0, so we graphed that one equation and we found the x-intercepts. In this case, we have two different equations, one on either side of the equal sign. So we can write them in as two separate equations, but now we'd find the points of intersection of these two graphs. We could move the x and the 1 over to the left side. We can subtract x and add 1 to both sides, and then it would be like the first example where we found the x-intercepts, because then you'd have one equation equal to 0. But the way this one is presented, it's two different equations, so you can put them both in, and you can see that there, it looks like there are 2 points of intersection. Second function trace, number 5 for intersect, enter, enter, enter. So the first one is at negative 0.43, approximately, because we're rounding. And our second one is at 3.097, or 3.10 if we round to the nearest hundredth. And so again, in this case, our answers were irrational, so we had to round them. The nice thing about doing it algebraically, though, is that we'll be able to state our answers as exact values. And sometimes you're asked to do that. Give answers as exact values. So we want to solve this algebraically. There's only one denominator here, which is 3 minus 2x, so we would multiply both sides by 3 minus 2x. So this shows me multiplying the left side by 3 minus 2x, and then we'll do the same thing on the right side. And the reason we're doing that is so that on the left, those 3 minus 2x's cancel. We no longer have denominators to worry about. If we multiply out on the right, and then I'll make it equal to 0. I'll add the 2x squared to both sides, so it'll give me 3x squared on the left. On the right side, I have a 3x and a 2x, which is a 5x. If I subtract that from both sides, I'll get negative 8x over on the left. And then we have a negative 3 that we'll add to both sides, which will give us minus 4 on the left. So there's the quadratic that we're now going to solve. And normally we solve these by factoring, but this one can't be factored. Okay? This one is not factorable. You can find 3x and x to multiply together to get the front term, but there's no combinations of numbers that you can find that multiply to get -4, and also when you multiply out the outer and inner terms, that would also give you minus 8x in the middle. So that's fine. It just means that we can't solve by factoring. That's where we use the quadratic formula. And it's on your formula sheet for the diploma exam. Negative b plus or minus the root of b squared minus 4ac all over 2a. Where a is the coefficient of the x squared, b is the coefficient of the x term, and c is the constant. So the value of b is -8, so negative b will be -8 or +8, plus or minus the root out. -8 squared will be 64 minus 4 times a, which is 3, times c, which is -4, all over 2 times a, or 2 times 3. So let's figure out what the discriminant is. Remember, that's the name given to what's under the radical. By going 64 minus 4 times 3 times -4. The discriminant is 112. That's the number under the radical. All over 2 times 3, which is 6. And you might remember that to simplify this, we need to reduce the radical. We cannot cancel right now. We cannot divide top and bottom by 2. We just divide the 8 and the 6 by 2. The top is a binomial. There's 2 terms there. So in that case, you have to be able to divide all the terms by the same factor, not just 2 of them. But we can do that by reducing the root 112. So remember, to reduce radicals, you want to find 2 numbers that multiply to give you the root of 112. But the key is that one of them must be a perfect square. So just looking at that, I know that 4 will divide into 112. So 112 divided by 4 is 28, which is also divisible by 4. So dividing by 4 twice should be the same thing as dividing by 16 once. I'm trying to find the largest perfect square that divides evenly into 112, and 16 would be the largest perfect square. 16 times 7 is 112. So write this as root 16 times root 7. The square root of 16 is 4. And now I can divide all the terms by 2. Now all 3 terms are divisible by 2. So that is the exact answer for the 2 x-intercepts, the 2 solutions, the 2 zeros, the 2 roots of that equation. Those are the exact values. We already know what they are as decimal equivalents. We found them to be -0.43 and 3.10. So we can check. We can put these 2 answers into our calculator to make sure. So the first one will be 4 plus 3 root 7, all in brackets, divided by 3. Whoops. Oh, yeah, it should be 2. Yep, thank you. Let me fix this, though. It should be 2 root 7. Absolutely. Divided by 3. So that gives us a 3.1 answer that we got on our calculator. Our second one, the -0.3, would be found by changing that plus 2 root 7 to a minus 2 root 7. And there's your -0.43 answer that we got. Okay. But doing it algebraically, we can write our answers as exact values. Whereas sometimes using the calculators, you get irrational answers that have to be rounded. All right, so in this case here, again, we're asked to solve this equation, graphically express answers to the nearest hundredth. And because I have two different sides, a left and a right side, I'll use two different equations. I'll put the left side into equation 1, 2 minus, in brackets, 3x over 2. The second equation is rational, so I'll use brackets to keep the numerator and denominators together. 1 plus 4x minus x squared divided by, in brackets, 4x plus 10. Just checking one more time to make sure I got everything right. Yep. So it appears there are 2 points of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. It gives me 1.14 if I round that one off. And the second one, enter, enter. I'll put my guess at, let's say, -5. And it's actually -3.34. Rounded to 2 decimals, to the nearest hundredth. And then it says to do this algebraically. And so normally we do this by multiplying all the terms by the common denominator. There are some times, though, you can factor to do some canceling to make it a little bit easier. But in this case, that's not possible. You cannot factor the 1 plus 4x minus x squared. You could factor a common factor of 2 out of the bottom here, 2 bracket 2x plus 5, but it doesn't help us at all. So we'll just go straight to multiplying all the terms by the least common denominator. And in this case, we do have two denominators, 2 and 4x plus 10. But 2 divides into 4x plus 10. So we only have to multiply everything by the 4x plus 10. So the first term is just 2. That's multiplied by the 4x plus 10. 3x over 2 is multiplied by the 4x plus 10, as well as the term on the right. Everything gets multiplied by 4x plus 10. Oh, thank you. So the whole point of doing that is so that those 4x plus 10s cancel on the right, but also this 2. 2 divides into 4x plus 10. You divide both of these terms by 2, which will give us 2x plus 5. And you also could have done this making out a common factor of 2 out of this 4x plus 10, and you would have been left with 2x plus 5 inside the brackets when the 2's canceled. Okay, so let's multiply what we have left. We'll have 8x plus 20. Then it's -3x times 2x plus 5, which will be -6x and -15x equals 1 plus 4x minus x squared. And I'm going to move everything from the right side over to the left side so I can make the x squared positive. But maybe before I do that, let's do some simplifying here. On the left, we've got 8x, take away 6x, which is 2x. Take away 15x, which is negative 13x, so it'll be 20 minus 13x on the left, equaling 1 plus 4x minus x squared on the right. So now I'll bring everything over to the left. And the reason I want to do that is to make the x squared positive. When you subtract 4x from both sides, you're going to get minus 17x. And when you subtract 1 from both sides, you're going to get plus 19. Oh, you were right. Yes. Thank you. Need to slow down a little bit here. Making too many mistakes. Thank you. So because of that then, I would move the 6x squared over to the right side. So negative 1x squared plus the 6x squared is 5x squared. I have 8x, take away 15x, which is negative 7x. I'm going to add the 7x to both sides. And on the right side, 4x plus 7x is positive 11x. And then when I bring the 20 over by subtracting 20 from both sides, I'll get minus 19. And so there is the quadratic that we now need to solve. And once again, that is not factorable. I'll tell you right now, it won't factor. The hint for that is because we know that our answers above were irrational. We found them on the graphing calculator. They were decimals we had to round. That means that your answers are not integral or rational. They're irrational. That is why this cannot be factored. If it could be factored, your answers would be either integral or rational, but they weren't. They were irrational. So that's a hint, a reason why you can only do this by the quadratic formula. It's not factorable. So our b value is positive 11, so negative b is negative 11 plus or minus the root of 11 squared is 121 minus 4 times a, which is 5, times c, which is negative 19, all over 2 times a, 2 times 5. So if we find the value of the discriminant, which remember is the number under the radical, 121 take away 4 times 5 times negative 19, the discriminant is 501. So this becomes negative 11 plus and minus the root of 501. And I don't think that can be reduced. I don't think there's any perfect squares that divide into 501. 501 is divisible by 3, but I don't think that helps us. No, 167 is not a perfect square. So those are our exact answers. And so we can check them against what we found graphically. In brackets, negative 11 plus the root of 501, all divided by 10. There's our 1.14 answer that we got. And if we change the plus root 501 to a minus root 501, there's our negative 3.34 answer that we got. But again, doing it algebraically, we get exact answers. All right. So for number 3, we were asked first to do it algebraically and then graphically. If we look at the denominator on the right of 4x plus 10, There's a common factor of 2 that we can take out of that, which gives us x plus 5. That's not the same thing as 2x plus 5, though. I'm sorry, it is, because a common factor of 2 gives us 2x plus 5 inside the brackets. So our common denominator, our least common denominator, would be 2 bracket 2x plus 5. We're going to multiply all 3 terms by 2 bracket 2x plus 5. So this shows multiplying that first term of x over 2x plus 5 by 2 bracket 2x plus 5. This shows multiplying the second term of 2x by 2 bracket 2x plus 5. And this shows multiplying the right side by 2 bracket 2x plus 5. And note that I wrote the denominator on the right side in the factored form, so it's easier to see that they cancel. But before we get there, we can just cancel the 2x plus 5s on the far left, and then we can divide top and bottom by 2 and 2x plus 5 on the right. So if we multiply what we have left, it's 2 times x plus, I'm going to do 2 times 2x, which is 4x, multiplied by 2x plus 5. So 4x times 2x is 8x squared, and 4x times 5 is plus 20x. And on the right side, I'm just left with 8x plus 15. So I'll bring everything over to the left side because the x squared term is positive. I have a 2x and a 20x, which is 22x. Subtract the 8x. 22x, take away 8x. Is 4x? No, 14x, I'm sorry. And then I'll bring the 15 over, and it's a minus 15 equals 0. And this one actually can be factored. And we would have seen that if we would have done it graphically first, because we would have found that the solutions were rational numbers, fractions. Okay? But this one can be factored. The factors are 2x plus 5 and 4x minus 3. The front term is multiplied to get 8x squared. The last term is multiplied to get negative 15. The outer product is minus 6x. The inner product is plus 20x. 20x minus 6x is our positive 14x in the middle. So the solutions come where each factor equals 0 then. So you'll subtract 5 on both sides and divide by 2. And then for the second factor equaling 0, we add 3 to both sides and divide by 4. So negative 5 halves, negative 2.5, and 3/4 or 0.75 are the two solutions. So they should be the two x-intercepts. So the left side, and again I'll use brackets here to keep the rational expression together. X divided by, also in brackets, 2x plus 5. Close the bracket on 2x plus 5. Close the bracket on the rational expression, plus 2x. And then on the other side, it's going to be 8x plus 15. In brackets divided by 4x plus 10. Is it okay? So we can see there are 2 points of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. There's our 0.75, our positive 3/4. Second function trace, number 5 for intersect. Enter, enter. If I put my guess at -2, there's my negative. Whoops, didn't go far enough over. Try it again. Second function trace, number 5 for intersect. Enter, enter. -2.5. That's weird. I'll try that. Should have worked though. Still doesn't. So maybe that's not a point of intersection. Maybe this is an extraneous root. Let's have a look here. If I make my windows, make my Y max a little larger, let's say 15, and a scale of 2. Maybe that's not a point of intersection. So we have a couple options for zooming here. I'm going to show you, if you hit zoom, the number 1 choice in here is zoom box. So when you hit that, we can move this cursor. See how it's moving? So wherever I press enter, that's going to be one corner of the box that I'm going to draw or open up. And then when I hit enter again, I can do that. So I'm going to hit enter there. And now I move the cursor again, and it's starting to open up this box. So right now it's just a line because I'm going straight up. But if I now start going to the left, it starts opening up this box. And I open up that box as much as I want. Maybe go a little bit higher. And then when I hit enter, it'll just redraw the portion that's inside the box. See, it doesn't really look like those two cross. So what that tells us then is that the -5/2 is an extraneous root. If we checked it in the equation, because that's the other way of knowing, right? That's the other way of knowing. Check it in the equation. So the left side, if I let x equal -2.5. So I'm going to use brackets here because I've got a rational expression. It's -2.5 divided by, and in brackets, 2 times -2.5 plus 5. So here I'm letting x equal -2.5. So that is the x over 2x plus 5. And I'll close the bracket on the rational expression, plus 2x, or 2 times -2.5. So that, whoa, I don't, oh, you know why? Because -5/2 is a non-permissive value, that's why. Because of the denominator of 2x plus 5, if you find the restriction on x there, it'll be -2.5, -5/2. That is the 0 of 2x plus 5. So it doesn't even work when we're checking because it is a non-permissive value. All right, so this -5/2 is extraneous. Our only answer is positive 3/4. So both methods work. And in this case, it wouldn't matter which way you did it because the answer is a rational number. So there's no really advantage to doing it algebraically because we could have found the exact answer using the graphical method unless you're asked to determine algebraically, or in this case, solve algebraically. Then you got to show your work. Right, same thing with this next one. I can factor out a common factor of 2 out of the 2x minus 6, which will give me x minus 3. And if I take out a common factor of -1, that'll also give me x minus 3. So this tells me that my least common denominator would be -1 bracket x minus 3. Actually, that's not true. Negative 2 bracket x minus 3. Because all the denominators have to divide evenly into it. So my least common denominator here would be negative 2 bracket x minus 3. X equals 3 will be non-permissive. So this is showing that I'm multiplying the left side by negative 2 bracket x minus 3. I have to multiply the 2x by negative 2 bracket x minus 3 minus, and then negative 2 bracket x minus 3 times x over negative 1 bracket x minus 3. So this is showing that I'm multiplying all of the terms by the common denominator of negative 2 bracket. Yes? Are you talking about right here? Your common factor is 2, and it's going to be 2 bracket x minus 3 here. Where do you see that? Here? Because my common denominator is negative 2 bracket x minus 3. Here's the positive 2x right there. I'm multiplying all the terms by negative 2 bracket x minus 3. But all the denominators have to divide evenly into it. So the well, it doesn't really matter. This is going to work, I'm sure. Because when you divide this negative 2 by a positive 2, that's going to give us, yeah, I see what you mean. But the thing though, I'm multiplying every term by the same value. So it'll work. As long as you multiply everything by the same thing. I guess I didn't have to multiply by the negative. I could have left that as a positive. It still would have worked. But because I am multiplying everything by the same value, it's correct. It'll work. It just means that this first part's going to be negative and this last part's going to be positive. Had I done it the other way, then the first part would have been positive and the last part would have been negative. But I'm multiplying everything by the same thing, so it will work. So these 2's cancel, these x minus 3's cancel. Negative 2 divided by negative 1 is positive 2, and the x minus 3's cancel. So if we multiply out what we have left, we have this negative sign in front times x plus 3. That'll be negative x minus 3 equals, here, this is going to be negative 4x. The negative 2 in front times the 2x at the end is negative 4x times x is negative 4x squared. And then negative 4x times negative 3 is plus 12x. And then this last part, you're going to have a minus 2 times x, which is minus 2x. So if we add the 4x squared over to the left side, it's a positive 4x squared. I'm going to subtract 12x from both sides, so negative 1, actually that's not true. I have 12x take away 2x, which is 10x. So I'm going to subtract 10x from both sides, which give me minus 11x, and then the minus 3 stays there. And that is the correct quadratic. And once again, this one can be factored. front terms need to multiply to get 4x squared. The last terms need to multiply to get negative 3. If we put a plus 1 with the 4x and a minus 3 with the x, the last terms multiply to get negative 3. The outer product is negative 12x. The inner product plus 1x. Negative 12 plus 1 is negative 11x. Now, if you have a hard time finding factors, that's fine, because you can still use the quadratic formula. It'll give you the answers using the quadratic formula. Factoring is generally easier if factorable, but sometimes the factors are a little more difficult to find. So we'll get negative 1/4 and positive 3. And positive 3 is a non-permissive value. 3 is a non-permissive value, so that would be an extraneous root. The only one that should work would be negative 1/4, and we will confirm that graphically. So the left side is x plus 3 divided by 2x minus 6. The right side is 2x take away, and it will be x divided by, in brackets, 3 minus x. Just checking. Yeah, that looks right. So zoom 6, set our windows back to their standard settings. So clearly there's one point of intersection here, and over here there isn't, because x equals 3, I think, is a vertical asymptote for both of those graphs. Right? If we look at the equations, again, this is 2 bracket x minus 3. 3 is a non-permissive value. It doesn't cancel out. The x minus 3 doesn't cancel. That means that 3 is a vertical asymptote. And it's also a vertical asymptote for the right side as well. So there is only one point of intersection right here. Again, they don't cross here because both of these graphs are approaching the vertical asymptote. So just to confirm, the negative 1/4, there it is on the graphing calculator. Okay. So page 465, questions 2 through 4 is what you should be working on. I will post those solutions to Google Classroom so that you can check your answers. Yes. Yep.